Chapter 11, Section 4. We are going to look at some of the highlights on pages 1 and 2. Let's start with the definition of the cross product. The cross product is defined on vectors in 3 space. The definition that we have here is presented algebraically in the form of the determinant of a 3 by 3 matrix. The definition, we take the determinant of this 2 by 2 matrix, which is U2 times V3 minus V2 times U3. That gives you the coefficient of the I component of the cross product. Then for the coefficient of the J component of the cross product, there's a minus sign, and in linear algebra you learn why that's the case. Cross those out, and then you have U1 times V3 minus V1 times U3. And then for the K component of the cross product, cross out the column and the row in which K lies, and we take U1 times V2 minus V1 times U2. And this formula that we see here, that gives you the cross product of 2 vectors in 3 space. It's easy to show that I cross J is equal to K, but if you compute J cross I, you get negative K. And we see that the cross product operation, we didn't prove it, we just see an example here. The cross product operation is not commutative. In fact, it's called anti-commutative because of the factor of -1. What I want you to note is the cross product is defined only for 3-dimensional vectors. So let's do a little comparison here in note 3. We've looked at the dot product before. Now, for the dot product, you bring together 2 vectors of any same dimension. Most importantly, the output of the dot product of 2 vectors is a scalar. And in our class, the scalar is always a real number. Cross product is defined only for 2 vectors in 3-dimensional space. So you can say you're inputting 2 vectors in 3-dimensional space, and your output or your result is a 3-dimensional vector. This is important to know. The output of a dot product is a scalar. The output of a cross product is a 3-dimensional vector. We will look at some of the algebraic properties of the cross product. U cross V is equal to negative, in other words, -1 times V cross U. This is called the anti-commutative property. Any vector U cross the 0 vector is equal to the 0 vector, and U cross U, any vector cross itself, is equal to 0. If you know some linear algebra and you look back at our determinant definition, you know that from linear algebra, in particular, if any 2 rows are the same, and this would be the case for U cross U, the determinant is 0. There are other conditions which result in a 0 determinant, but in particular, if 2 rows are the same, the determinant of that matrix is 0. Here are some other algebraic properties of the cross product. There is a distributive property. Next, we have a property involving a scalar. And then we have an interesting property involving a dot product and a cross product. Let's get to some geometric properties of the cross product. Probably the most important one. U cross V is orthogonal to U and orthogonal to V. Secondly, U cross V equals 0 if and only if U and V are scalar multiples of each other. Now what if and only if means is the following. We have a two-way statement. In one direction, if we know or assume that U cross V is a 0 vector, then it must be the case that U and V are scalar multiples of each other. Or, if you start over here and you assume or know that U and V are scalar multiples of each other, it always follows then that U cross V equals a 0 vector. The magnitude of U cross V is equal to the magnitude of U times the magnitude of V times sine of theta, which is the angle between the two, where theta ranges from 0 to pi. Now remember that U cross V gives you a vector that is perpendicular both to U and to V. And in property number 3, we have a formula for the magnitude or the length of this cross product. As a number, the length of the cross product is equal to the area of the parallelogram as a number. Of course, a length is 1-dimensional and an area is 2-dimensional, so I wouldn't ever say that a length equals an area. But the length of this cross product vector as a number is equal to the area of this parallelogram as a number. And then lastly, we have here the volume of a parallelepiped with U, V, and W as adjacent edges.